Hello and welcome back to the lecture on applied econometry.
We have been talking about instrumental variable, and in this lecture we are going to deal with a particular concept called asymptotic property of regressor, and we're going to see why exactly this asymptotic property of regressor is helpful. And before that, we actually will see what exactly is this asymptotic property of regressor. Now, before I proceed to explain this idea, let me first write down a formula that we have been writing all throughout, and that is B2 OLS is equal to beta 2 plus summation xi minus x bar into ui minus u bar divided by summation xi minus x bar whole square, and this all numerator as well as the denominator is over all n. Now we're familiar with this formulation, and this formulation is important. Particularly this error term is really important in the sense that this error term actually gives a normal distribution of B2 OLS. This error term, this component of error is actually coming from the regression error, and we know that regression error is actually, it follows a normal distribution as per the Gauss-Markov assumption, and we know it follows normal distribution because the regression error is actually influenced by many regression, many variables which are not in the regression but actually influences the error. And since none of the variable has a dominating influence, so then we will have a normal distribution of the error term according to one variant of the central limit theorem. Now, since I have a part of this error term here, so this is also a normal distribution. Now, when I have this error term normal here, and I know that beta 2 is a population parameter, and that is basically a constant. So essentially, this B2 OLS is also going to have a normal distribution. Now, why is it important? It is important because if and only if I have beta 2 beta 2 OLS, B2 OLS is normal, then I can run things like t-test, f-test, and so forth, right? Now, having said that, we are going to actually see why exactly, how exactly is the asymptotic property and why exactly that is helpful. Okay, now let's think the population as something like this. Okay, so let's think how beta 2 and B2 OLS are related. Let's say this is our population, and let's say there is a population parameter B2. Okay, now you do not have the population, you do not have entire population with you, neither you have a specific value of B2. So what you can do, you can draw samples, right? You can draw these different samples, let's say, and you get the values. Let's say B2 OLS here, and you get a B2 OLS here, and you get a B2 OLS here, B2 OLS here, you get a B2 OLS here, and so forth. Now, never mind this part which has come out of the circle. Essentially, it means that the samples are drawn from this population. Now, I have all this B2 OLS, right? But I will have this B2 OLS values. Essentially, they will be different. And the reason why they will be different is the error term. Because the error term is present there for each of this different, estimation of B2 OLS. We are going to have this different random error, and that is going to give a different value. So B2 OLS will not have a fixed value like beta 2. Of course, B2 OLS contains beta 2, but along with that, it contains this error component. Now, if that is the case, now if I plot, so essentially what I'll get is a B2 OLS, a distribution of B2 OLS, right? So because this error component is normal, the distribution of B2 OLS is also going to be normal, right? I can say that safely, that the distribution of B2 OLS is going to be a normal distribution. Let's say this is the, you can plot probability density or frequency in the x-axis, y-axis, and the value of B2 OLS in the x-axis. Okay. Now, if we plot this, we will get a normal distribution. Now, when we actually talk about the asymptotic property, let me reduce the size a little bit. When I talk about the asymptotic property, by asymptotic means what happens when n tends to infinity. Asymptotic property means what happens to the regressor here when n tends to infinity. All right, so I'll try to see that. Now we know for a fact that if n is large or if n is increasing, so what I'll have, my distribution of B2OLS will come close and close to the true value of beta, right, or beta 2 here. So if that is the case, so what I'll have is that I will have a narrower and a narrower distribution of B2OLS, and which is actually going to be close to our true beta 2. Okay, now so then it means that if I increase the number to infinity, I am actually going to get a better estimate. Now that is important. Now if I want to now actually use this formulation, I cannot. So previously when I was estimating this B2OLS, I was actually taking expectation value on both the sides. But here when n is infinity and actually the with more complex relationship, I will have a formulation of limit. Okay, I'll take limit instead of expectation on both the sides. So what I'll do, I'll write plim B2 OLS is equal to, you can take plim beta 2 and you will take, let's reduce the size a little bit, plim on the numerator summation of xi minus x bar and ui minus u bar. In the denominator you again take plim, but in this case you are going to take summation of xi minus x bar whole square. Now what I'll get, so plim of beta 2 is constant, so it is going to be beta 2. Now what I get in the numerator denominator, we don't get anything from this formulation, because as I increase n, as I keep on increasing n, so what will happen is that I will have larger and larger values. So I will not come to any convergence, but I want some convergence. Okay. Now if you see, if I can actually multiply both numerator and denominator with 1 by n, so I can actually come to some result. If I can multiply with 1 by n, so I will come to some result, and the result on the numerator is going to be the covariance between x and u, whereas the result in the denominator is going to be the or the variance of x. Okay, so I will write that 1 by n summation of xi minus x bar. So essentially that is going to be beta 2 plus covariance xu and variance of x. Okay, so this is the application of plim, and this is the result. Now you may wonder, previously we used expectation rule and we got result same as what you got using plim, but why exactly we bother about using plim? Now the reason is that, as I mentioned previously, is that sometimes what happens is that when I go into the paradigm of stochastic regressor and the formulation becomes complex, we need, with the expectation rule does not work anymore. So we need something more powerful, more robust, and that is why we use plim. Now previously we have been using non-stochastic regressor, and it was absolutely fine to use the expectation rule, but now we are into the domain of stochastic regressor and we see the problem of endogeneity. And when we talk about instrumental variable, we will solve the problem of endogeneity, which is essentially a complex relationship between the regressor as well as the error term. We're going to talk about the endogeneity in the next lecture. So essentially, because of this complex relationship that we have between the xi's and the error terms, so we need to use plim. So that is basically the reason why we need to use plim. And we'll see the application of asymptotic property of the regressor going forward. So with this, we end this lecture here. Thank you.